Force on a current carrying conductor. Force on a current carrying conductor placed. Force on a current carrying conductor placed in a magnetic field. Force on a current carrying conductor placed in a magnetic field. This is a cylindrical wire and we can denote the axis of this cylindrical wire. The dotted straight line as shown in figure is the axis of this cylindrical wire. X1, X2 is the cylindrical wire having length L. L is the length of the cylindrical wire X1, X2. L is the length of the cylindrical wire. And here we can denote a free electron of charge QE equal minus E, which is situated on the axis of the cylindrical wire, and we can denote three-dimensional axis or three axes, X, Y, and Z axis. X, Y, and Z axis. The vertical axis is Z axis. This is Z axis and we can denote Y axis in the diagram. We can denote Y axis in the diagram and also X axis. This is Y axis and the horizontal axis is X axis. X axis and Y axis exist in horizontal plane and Z axis is perpendicular or is situated in vertical direction, and current I flows through this cylindrical wire X1, X2. This current I flows from the end X1 to X2. That means current flows towards right. And magnetic field induction B acts inwards. That is, this magnetic field B acts along Y axis as shown in the figure. So this is magnetic field induction B, which acts inwards at an angle theta. This magnetic field induction B acts at an angle theta with the direction of flow of current I. As the current flows towards right along positive x-axis, a free electron on the axis of the cylindrical wire will be accelerated with a drift velocity Vd in the opposite direction of current. That means this electron will be accelerated with the drift velocity Vd towards left. And in this case, as this electron is moving with a certain velocity in a magnetic field, in a direction perpendicular to magnetic field induction, in that case this free electron will experience a magnetic Lorentz force Fe, and this magnetic Lorentz force experienced by the free electron will act vertically downwards. This magnetic Lorentz force experienced by the free electron acts vertically downwards. As n number of free electrons of the conductor experiences magnetic Lorentz force which acts vertically downwards, that's why the conductor X1, X2 will experience a force F in vertically upward direction. The conductor X1, X2 carrying current I placed in a magnetic field B acts a force in vertically upward direction. Let X1, X2 be a long straight conductor. X1, X2 be a long straight conductor of length L, and area of cross section A. An area of cross section A carrying a current I, carrying an electric current I, and carrying an electric current I, bracket closed, which is placed along x-axis in horizontal direction, in a uniform magnetic field of magnetic field induction B at an angle at an angle theta with the direction of the magnetic field induction B, at an angle theta with the direction of that magnetic field induction B. This magnetic field induction B acts inwards and along y-axis in xy plane or in horizontal plane. When an electric current I flows through the straight conductor x1 x2 flows through the straight conductor x1 x2 flows through the straight conductor x1 x2 from the end x1 to other end x2 of the conductor. That means the current flows through the conductor along positive x-axis. That means this current flows towards right through the cylindrical conductor or wire x1 x2. A free electron, when an electric current I flows through the straight conductor along positive x-axis, a free electron of the conductor will be moving from the index to x1 to x1 end of the conductor with a drift velocity Vd subscript D. Now in the diagram, current I flows towards right and free electron of the conductor will be accelerated with a drift velocity Vd. Magnetic field induction B acts along y-axis at an angle theta with the direction of flow of current or with positive x-axis. In this case, the magnetic Lorentz force experienced by the free electron of the conductor x1 x2. In this case, the magnetic Lorentz force experienced by the free electron of the conductor x1 x2 accelerating with a drift velocity Vd in the uniform magnetic field B is given by the magnetic Lorentz force experienced by the free electron of the conductor is given by Fe equal QE Vd B sine 180 degree minus theta. That is the expression of magnetic Lorentz force experienced by free electron when it is accelerated with a drift velocity Vd, where QE equal minus E, which is the charge of a free electron of the conductor x1 x2. QE equal minus E, which is the charge of the free electron. Now we can denote a free electron of the conductor. E is the free electron of the conductor. And we can denote the direction of current. That means current flows towards right and the free electron will be accelerated towards left with a drift velocity Vd. Magnetic field B acts inwards in horizontal plane, that means in xy plane, and magnetic field B acts at an angle theta with the direction of current flowing through the straight conductor. In that case, force experienced by the free electrons of the conductor, that is Fe, acts downwards. Angle between the direction of magnetic field B and drift velocity Vd is 180 degree minus theta, and QE equal minus E. Here in place of QE, we have to write E, considering the magnitude and no need to consider the sign of charge. That means E Vd B sine 180 degree minus theta. Fe equal E Vd B sine 180 degree minus theta. Though QE equal minus E, QE equal minus E, comma, the sign of the charge is not put in the expression of the force. That is, sign of the charge is not used in the expression of the force Fe equal QE VdB sine theta or sine 180 degree minus theta. Though QE equal minus E, the sign of this charge, that means this negative sign, will not be put or will not be used in the expression of the force. Here we have written E instead of minus E. QE was minus E, but here we cannot use the sign of charge. That's why negative sign is not used in the expression of force. So therefore we get Fe equal E Vd B sine theta. E Vd B sine theta. Because sine 180 degree minus theta is equal to sine theta. We get the expression of the force experienced by a free electron, that is Fe equal E Vd B sine theta. This is the magnetic Lorentz force. On the free electron of the conductor X1, X2. This is the magnetic Lorentz force on the free electron of the conductor X1, X2. And it acts downwards, that is along negative z-axis. This force acts downwards along negative z-axis. Therefore, the total force on the conductor X1, X2 carrying a current I placed in a magnetic field is given by F equal total number of free electrons into magnetic Lorentz force experienced by a free electron of the conductor. Magnetic Lorentz force experienced by a free electron or comma F equal to NFE or comma F equal NE Vd B sine theta. That means force experienced by the conductor will be equal to the magnetic Lorentz force experienced by n number of free electrons. Now F equal NE Vd B sine theta. In this case, from equation 1, Fe was NE Vd B sine theta. That's why you have written F as NE Vd B sine theta. In this case, magnetic Lorentz force experienced by a free electron acts downwards, and force experienced by the long straight conductor X1, X2 will be acting upwards. This is a conductor, and a free electron will be accelerated with a drift velocity Vd towards left, and current I flows towards right. A magnetic field B acts inwards, and magnetic Lorentz force experienced by a free electron will be acting downwards, and force experienced by the conductor will be acting upwards. Now the current flowing through the conductor X1, X2, through the straight conductor X1, X2, and under bracket of current we can write I. The current I flowing through the conductor X1, X2 is related with the drift velocity of free electron, with the drift velocity Vd of free electron, by the relation is related with the drift velocity of free electron by the relation I equal Vena, where Vd is the drift velocity of free electron, small n equal capital N divided by A dot L. So now this end of the conductor has the area of cross section A. L is the length of the conductor. A current I flows through the conductor towards right. In this case, small n equal n divided by A dot L, which is the free electron density or number density of free electrons of the straight conductor x1 x2. Small n is the number or density of free electrons of the conductor x1 x2. Small n is total number of free electrons, that is n, divided by volume of the conductor, that is A dot L. Or comma Vd equal I divided by ENA. Vd equal I divided by ENA, which is equation 3. Equation 3. Vd is the drift velocity of a free electron which is accelerated with a drift velocity Vd in a direction in the opposite direction of flow of current. Therefore, F equal NE Vd B sin theta equal NE I divided by ENA dot B sin theta equal, now in place of n or in place of total number of free electrons we can write small n A dot L E dot I divided by NA B sin theta. So finally we get ILB sin theta. F equal, therefore F equal ILB sin theta, which is the force experienced by a current carrying straight conductor placed in a magnetic field. F equal ILB sin theta. This is the force on the current carrying straight conductor x1 x2 straight conductor x1 x2 placed in a magnetic field B. F equal ILB sin theta. This is the force on the current carrying straight conductor x1 x2 placed in a magnetic field. Therefore F equal I vector L cross vector B. Vector F equal I vector L cross vector B according to Fleming's left hand rule. According to Fleming's left hand rule, this force vector F equal I bracket open L vector L cross vector B bracket closed. According to Fleming's left hand rule, this force, that is vector F equal I vector L cross vector B, experienced by the current carrying straight conductor x1 x2, experienced by the current carrying straight conductor x1 x2 placed in a magnetic field under bracket vector B acts, that means this force acts upwards perpendicular to the straight conductor x1 x2. This force acts upwards, that is along z-axis provided the conductor x1 x2 is placed along x-axis and magnetic field induction under bracket vector B acts inwards, that is along positive y-axis. Magnetic field B acts along positive y-axis. This is the long straight conductor or straight conductor carrying a current I. We can denote the axis of the conductor. L is the length. Or vector L is the length vector of the conductor, and the conductor x1 x2 is placed along x-axis. And a magnetic field acts inwards, that means this magnetic field induction vector B acts along y-axis. If we denote z-axis, in that case force vector, that is vector F experienced by the conductor carrying current I, acts along positive z-axis. As vector F equal I vector L cross vector B, we can say that this force experienced by the conductor will be perpendicular to length vector and will be perpendicular to magnetic field induction vector. That means vector F is perpendicular to B and vector F is perpendicular to vector L of the conductor. Therefore F equal ILB sin theta. That is the force experienced by long straight conductor. And here vector F is not equal I vector B cross vector L, but here vector F equal I vector L cross vector B. Vector L is the length vector which appears earlier in the expression, and vector B comes later in the expression. So if we draw the straight conductor, and this is the axis of the conductor, a current flows through the long straight conductor or straight conductor, and current flows and vector L or length vector acts towards right in the direction of current, and vector B, magnetic field induction vector, acts inwards. And vector L is the own physical quantity of the straight conductor x1 x2. Vector L is the own physical quantity of the conductor x1 x2, and vector B is the external physical quantity. Magnetic field induction is the external physical quantity, and length vector is the own physical quantity of the long straight conductor. Hence vector L appears earlier and vector B comes later in the expression of force, or vector F. Therefore vector F equal I vector L cross vector B. This is the force experienced by a current carrying long straight conductor placed in a magnetic field, that is vector F equal I vector L cross vector B.